An analog log10 computer circuit is shown here, implemented with two operational amplifiers and a pair of bipolar junction transistor, or BJT, as you can see here, that are matched. We want to see how this circuit is working, and we want to see if Vin is applied at the input of a circuit as an input voltage, then how the circuit realize an output voltage that is proportional to logarithm of the Vn, effectively calculating logarithm of the input voltage. It can realize log base 10 or natural logarithm or log 2, whatever desired. I'm going to show. So let's check the circuit. Let's make the assumption that the supply voltages like plus minus 10 volt are properly applied for both op amp 1 and op amp 2. And as you can see, for both op amps, what we have is the output of op amps via feedback is connected to negative or inverting input terminal. Therefore, negative feedback is there as well for both op amps. So op amps are properly biased. And they are with negative feedback. And as a result, they are in linear region of operation. And because of that, I can make the assumption that the virtual short is valid for both op amps. So virtual short is valid, and that enforces that voltage at positive input terminal or non-inverting terminal of each op amp is equal to voltage at negative terminal. And in the case of op amp 1, so I'm going to keep this as equation 1. In case of op amp 1, you can see that the positive terminal or non-inverting terminal via this matching resistor R is grounded. So the voltage here, assuming ideal op amp with practically zero current and practically infinite input impedance, you can see that the voltage here is 0 volt. Because of virtual short equation 1, this negative terminal is also forced to be at 0 volt, which means virtual ground. So virtually grounded effectively. And therefore, as a result, the voltage drop across this resistor R, or input resistor here, is just Vn and 0. So therefore, we can compute the current that is going this way. And that current is simply I equal to Vn divided by R. Okay, so that's interesting, but the other observation is this current cannot go through the input of op amp, because input of good design, well-designed op amp, it has practically infinite input impedance, so this current has only one way to go, which is this way toward the collector of transistor T1. It's important to note that transistors T1 and T2 should be matched. They should be on the same substrate, and they should be very close to each other so that they have exactly same junction, p-n junction properties and also thermal properties. That's important. So they should be in the same package, same substrate, same junction property. Alright, with that in mind, IC1, which is the collector, current of the collector of transistor 1, is now equal to I, and as you can see is equal to Vin over R. So I'm going to write it here. I'm going to write IC1 is equal to I equal to Vin over R. Let's name that as equation number 2. Okay, so the other thing I can compute is also I can compute the current that is going this way from the reference voltage Vref 10 volt, which is important, through the 10R resistor. By the way, the value of these resistors can be set practically like 10 kilo ohm for this resistor, 10 kilo ohm for this one, naturally 10 times that, 100 kilo ohm for this resistor, and I'm going to talk about the value of these two resistors as well. This 1 kilo ohm resistor at the output of op amp 1 is for practical reason to increase the stability of the circuit, because it's not a good idea, generally speaking, to apply directly the output fast moving voltage of the output of op amp to emitter, which is directly then connected to directly controlling VBE of transistor that is exponentially affecting the current. So it's not a good idea. So that's why we usually have this relatively small resistor there as an enforcer of the stability. Alright, so that's the only reason for that. let's find this IC2, because this current that is going through the resistor 10R effectively mainly becomes the current of collector and of course current of emitter. For both transistor T1 and T2, we make the assumption that beta, which is the current gain of transistor, IC over IB, so IC over IB, we make the assumption that this parameter for both transistors is pretty large. So it's much larger than 1. It's a reasonable assumption. These transistors are not high current transistors, therefore they will having large beta is not strange, like 100, 200. Okay, so let's compute then what is this current, say IC2 or I2. Okay, this I2 for transistor 2 is simply 10 volt minus this voltage, which is Vx, voltage at the positive terminal of op-amp 2, so V reference, so Vref, let's say, and minus Vx divided by the 10R, which is for example 100 kilo ohm. Okay, so the next move is just let's keep the Vref is 10 volt. The Vx, I have a quick comment about it practically compared to 10 volt. So VB of a transistor during nominal operation is on the order of 0.6 to 0.8, nominal 0.7, hardly get to 0.8. So that's the range. The same thing applies to this one as well, between 0.6 to 0.8. So the voltage here, let's say this T1 is roughly 0.7. This one is nominal 0.7 as well. So with the variation expected, this Vx at the base of transistor 2 is not going to be more than plus minus, say, 0.1 volt or so. So it's changing in that ballpark, is nearly 0. So with the proper selection of Vref at 10 volt, which is nearly 100 times what is expected to be the variation of the voltage of base of transistor T2, we can make the assumption that this equation effectively is just simply, so I'm going to write it this way, because Vref is much greater than Vx on the order of 100 times. This equation is roughly equal to just Vref divided by 10R, which in this case is 10 volt divided by 10R. So let's keep that here for now. That is the current equation for the current of transistor T2. Now let's also write, I'm going to show plus minus VBE 2. So let's put it this way, VBE 2, and I'm going to write it this way, plus minus VBE 1. And notice that the V base of transistor 1 is 0, of course, because it is grounded. Okay, so if I write a KVL from Vx this way, so from Vx, if I write a KVL to get to ground, so basically what I'm doing is writing a KVL like this and then getting to ground. I can write voltage of X, which is voltage of, or let's put it this way, voltage of positive terminal of op-amp 2, this terminal, is equal to voltage at node X, which is that node, is equal to voltage of base of transistor 2, is equal to, as you can see, a drop of VBE2, so VBE2, and then with the polarity that is assumed for the base emitter of transistor 1, then I am saying minus VBE1 to get to base of 1, which is ground. So okay, so that is the KVL effectively, or Kirchhoff voltage law, that I just, one of the circuit laws that I just wrote. So as a result, I can say Vx is equal to just VBE2 minus VBE1, equation 2, or let's say 2 and 3, so equation 3. This one, I need therefore to just replace VBE of the voltage of base emitter or PN junction of the transistors. For that, I am going to use Shockley, the well-known junction current voltage equation, so Shockley p-n junction equation that is applicable for bipolar transistors as well, which for that I can say the voltage of junction, in this case base emitter, is equal to eta, ideality factor of transistor, times the thermal voltage Vt times natural logarithm of the current of collector of transistor divided by the saturation current of transistor. In this equation, eta is the ideality factor, so this one is ideality factor. It's a value between 1 and 2. It's safe to say, we can assume practically in one example that it is just equal to 1, for example, practically. There are transistors, many transistors with eta 1, there are transistors eta 2. So ideality factor, I'm going to make the assumption eta is 1. Okay, what else? Vt is the thermal voltage of the p-n junction, thermal voltage, and this Vt is just equal to kT over Q. K is Boltzmann constant, so in that regard I have a reference just for the sake of making sure we know this K and Q. So K is the Boltzmann constant, it's well-known constant, and Q is the electron charge, very small, 1.610 to the negative 19 joules per Kelvin, and T is the temperature of the junction of these transistors inside the same package. That would be the same for both of them because they are sitting very close to each other on the same package, on the same substrate. So this T is temperature in Kelvin. For example, room temperature 27 degrees C translate to 300 Kelvin. With that and these constants K and Q, if you substitute, you get to Vt, which is this thermal voltage, to roughly about 26 millivolt at room temperature. Temperature of 27 degrees C. Okay, so with that in mind, I can now just move on and say, okay, I assume eta is 1, and I assumed Vt is 27 millivolts. So my equation, my Shockley equation, becomes for p-n junction 26 millivolt times ln I natural logarithm, so times natural logarithm current of collector divided by saturation current. Okay, so this is important. This equation is what I needed actually, which defines the voltage of base emitter as a function of the current of the collector of transistor. One important reminder, you can see that Vt is linearly proportional to temperature, absolute temperature in Kelvin for junction. Is is the most dangerous one. This one is exponentially dependent on temperature. So Is is exponentially varying. So exponentially changing with temperature, and if temperature changes, let's say 10, 15, 20%, Vt changes 10, 15, 20% from nominal 26 millivolt, but Is changes on the order of 5 to 10x. So that's very dangerous. We want to get rid of that dependency. So that dependency here results in a circuit that the output or the result of it is becomes not much accurate. So that's why dependency on that in this circuit is resolved. How? Using this pair of p-n junction that I'm going to show. So let's go back to equation 3 and substitute for VBE2 and VBE1 using the Shockley current voltage equation that I just discussed. So this is equation 4, and I'm going to apply it to what we just talked about. So I am going to therefore say Vx, so let's say applying equation 4, or substituting using result from equation 4, applying 4, we get Vx is equal to VBE2 now is 26 millivolt times ln IC2 divided by Is minus, I can factor out 26 millivolt, ln IC1 over Is. Again, both transistors, very important that they are matched p-n junction wise on the same substrate, so they have the same IS and same temperature dependency, because now we can get rid of that dependency. Because benefiting from the properties of logarithm, it become IC2 divided by IS divided by IC1 divided by IS. And as a result, IS cancel out, which is exactly what we wanted, assuming transistors are well matched. So hence, I get Vx equal to 26 millivolt natural logarithm of IC2 over IC1. Now, I can substitute using equations 2 and there was another equation here. Instead of saying 1 is the virtual short, let's keep this one as 1 because we have another 2. So let's keep this one as 1. Therefore, using equation 1 and 2, by 1 I mean this one on top that defines IC1, and by 2 I mean this one that defines IC2. So I'm going to use them and substitute IC2 and IC1 here in this equation. So 26 millivolt ln, and IC2 is the numerator. I'm going to show it in a better and clear way. So IC2, and it's 10 over 10R, so it's going to be, let me change the color, okay, so it's 10 over 10R, and for IC1, I have from equation 1, Vn over R, so it will be Vn over R. Great. So what happens is now I get rid of this dependency on these two resistors. R cancel out. By the way, just as a reference, as I mentioned, these can be 10 kilo ohm selected, and these resistors here, 10R, can be set to 10 times that to 100 kilo ohm. So these are practical values. As I said before, this one is just for stability. As long as it's on the order of 1 kilo ohm or so is fine. We're going to talk about the value of these ones as well. Okay, so the result becomes what? The result becomes, so here's what we get for the result of this. 26 millivolt ln, and then we have effectively 10 and 10 cancel out and become 1 over Vn, voltage over voltage, so it's dimensionless inside the argument of natural logarithm. This can be also written then in the form of just 1 over, instead of ln of 1 over n, I can write minus 26 millivolt, the Vt, and then ln, so Vn. Great. So this is the super important equation number 5, I think, that I got to. Okay, what is the next step then? The next step is just dealing with this non-inverting last step amplifier op-amp topology that is shown here, because of virtual short, we just found the Vx, which is the voltage at positive input terminal of op-amp 2. Because of virtual short, that is the same as negative terminal. So therefore I can say voltage here at this node, voltage is also this value. So I'm going to just show it. There you go. So it's going to be Vx, which is what we found in this equation. Now, since there is no current going in or out of the input terminal of ideal op-amp, practical op-amp well designed because it has practical infinite impedance, these two resistors, RF and RN, are effectively in series. And if you have Vx here that define a current, I mean, it's a well-known equation of non-inverting gain of non-inverting amplifier. But basically what happens is there is this current IRN that is going through this, and that IRN, if I change the color so that it's clear which current I'm talking about, so this current is the same. IRN is the same as IRF. So therefore I can say V out is equal to RF in series with RN, the sum of two resistors in series effectively, times the current, and the current is Vx divided by Rn, because across Rn is only Vx. So Vx divided by Rn, which we can write it in the form of Rf over Rn plus 1 times, and then for Vx I'm going to substitute from using equation 5, so this equation, and I'm going to just write minus 26 millivolt natural logarithm ln of Vn. So in summary, if I just substitute and just reshuffle things, I get negative 26 millivolt 1 plus Rf over Rn and natural logarithm Vn. Great. So I proved this way. I managed to show that the circuit is really logarithm computer. So it does compute the logarithm of the input voltage, but it is natural logarithm. So the last step to just show how we can achieve any base logarithm that we're interested in is this step. I'm going to show that, so here, I'm going to show that, okay, V out is minus 26 millivolt, 1 plus Rf over Rn, and we know that ln is simply log base e. So what I'm writing here is log base e natural logarithm of Vn. So instead of writing log base e, I can write log base 10 Vn, and then I can multiply that by log base, let's say, E10. And this, so log base E10 or ln10, and ln10 is 2.3 roughly. So this one is roughly a fixed value, 2.3 roughly. And then 2.3 multiplying negative 26 give us roughly negative 60. So we get negative 60 millivolt 1 plus Rf over Rn log Vn base 10. Now the last thing, if I really want the circuit to just output voltage to exactly become equal to just log Vn 10, neglecting the negative sign, that doesn't matter, I can just adjust that using another inverting stage, then I need to set this 60 millivolt. Remember, this is 60 millivolt. So millivolt translate that this number is 0.06. So I need to set the gain of the circuit, basically Rf over Rn, in this formula, such that 60 millivolt, or let me just change the color, such that this value becomes 1. So to achieve that, I need 1 plus Rf over Rn to be about 16.7, or basically I need Rf over Rn to be about 15.7 roughly. So that's it. If I set Rn, for example, to 1 kilo ohm, I can set Rf to 15.7 kilo ohm, for instance, and that would get me to then, if I do it that way, if I decide that is what I want to do, then it roughly become minus log Vn base 10. So neglecting the negative sign, the circuit is computing base 10 logarithm of input voltage. If you want another base, you just make the adjustment properly in the value of Rf over Rn, or the gain of the non-inverting stage, which is the second stage here. I hope that this example is helpful in terms of showing how we can have a core of a, let's say, logarithm computer, analog computer circuit, functional, and then what sort of things we need to consider, and what parameters we can adjust in the circuit to get to the proper base in the logarithm that we are looking for. I hope this is helpful. Thanks.